Alright, how's it going, gamers? Jumpre here, and welcome to webisode 5 of our battle against vector spaces. So, this is quite a critical chapter in terms of all 6 that we're doing. So, I wanted to do so, I'm not done for any of the other episodes yet, but I want to do a quick preface section where we just talk about where we're at and the goal really of what we're doing. So, we've done chapters 1 to 3. I haven't recorded 1 and 2 at this point, but at some point they'll be done. They're less important. I just kind of go with some fundamental definitions from a slower perspective. Chapter 4 is on spanning sets, which we did before this one, and then today we take on Chapter 5 on linear independence. And essentially, the way I like to think about these topics, at least, is that they're all kind of building towards Chapter 6, which can be on basis. More on that later, don't worry. But essentially, 4 and 5 kind of directly build into Chapter 6 in terms of definition and proof-wise. And out of the 2 spanning sets, I think people tend to find a little easier. Mostly maybe because it's called linear independence, and so the definitions are quite precise and technical, a little difficult to carry around and remember, and also I think it's a little less intuitive than spanning sets. So to counteract this point of sometimes this getting neglected in terms of care taken over it, first of all, a lot of time went into this video. To the point of I don't even know if it was worth it, but maybe it is. And then the second thing is I've got this sort of notation / idea. Oh, I don't know why I didn't just drag it. I don't know why I copied it. Oh well, we're here now. In that we're gonna be using alpha flavored to refer to linear independent, and linear dependent to mean beta flavored. This is quite a bold idea, but in my opinion, they kind of do this in physics with the quarks, they call them charm, strange, etc. And the idea is you just give it an arbitrary label that doesn't really mean anything to try and suggest that you need to look at the definition, and that these words alone won't, because I think words are a lot clumsier and not as precise. So in respect to that, this is the approach I'm taking. I might re-record it without using these terms and just using the formal names, but this is an idea I had, and I'll cover it more in a second. So that's the first point I wanted to go over. That's all I wanted to say actually in the preface. So I don't know if I'll do this in future episodes, but I did get a message of someone saying that they thought this bit was a good idea. So in this thing we're going to be covering 10 items. So we're going to be doing a notation, a nomenclature, and then we're going to do a quick theorem, a quick corollary of that theorem, and then we're going to do the definitions, the key ones of independence and dependence, or alpha flavored and beta flavored. Then after that we're going to do the 2 big theorems of this chapter, this being the more important of the theorems that I'm going to strive to try and prove in a few episodes' time. And then after that we've got 2 less important items at the end, but just because I wanted to shove everything that I wanted to into this video, and hopefully still keep it under half an hour. That is the goal. I'm pretty certain it is, because this intro I don't think was any longer than maybe 3 minutes, so we should be good. Alright, that's it from the preface, let's go on to the video. Alright, and so we begin. So, oh, drawing tablet working? I think it is. Alright, cool, let's go. So, we're first going to look at a notation which might seem a bit simple to you guys, but I just want to make sure everyone's on the same page with the notation we'll be using. So this symbol just simply means does not imply, and the reason I'm covering it is because in this chapter, in this episode, we're just going to try and get all the content, and then we'll do proofs and worked examples in later episodes. So the 2 theorems, the 2 definitions we'll be looking at are going to be defining our main focus, linear independence. So we're going to have one definition for linear independence and the other for linear dependence. And for one of the definitions we're going to be using this symbol, so I just wanted to make sure it was extra clear, because I thought there were some slight logical subtleties of this which were worth going into. So, and I also want to give an example just to make it even clearer, which might seem unnecessary, but we're going to do it. So we're going to have the statement, I ate a whole cake in 10 minutes, and we're going to have does not imply I am obese. A fun example, but it has an important point, and the point is that just because you ate a whole cake in 10 minutes doesn't mean you're obese. We all get that, but it doesn't mean it couldn't be true. It could be that you ate a whole cake that quickly and you're obese. It's not necessarily the case, and this is a logical point we'll come back to, but I'll come back to it more when we look at I can't remember which definition it is. 1, 2, 3, 4, 5. So definition 5.6, we'll come back to this. And I just thought this concrete example would help when we get to that. I just wanted to put it so it's sort of selling it in the back of your head, hopefully, with a nice visual example. And so now we're going to move on to nomenclature 5.2, and so essentially we're going to be looking at basis next in chapter 6, and the plural of a basis, which the mathematical object will define next chapter. The plural for it, for some reason, mathematicians have decided bases. It looks like bases, but it's pronounced bases, and just because this chapter and also the one we did on spanning sets are going to tie into bases, I just wanted to make sure that it was like clear what the terminology was. And that's all on that. And then we continue onto a important theorem that will seem a little odd that I'm doing this here now. And proving this is like outside the scope, maybe episode 5 of this chapter, but in general, like, it's just sort of a given result. This is like a common linear algebra theorem, but I have a feeling that like it sometimes gets overlooked and it's really important, and we'll be using it in proofs for this chapter, which isn't this episode, but in a few episodes time we'll be doing some proofs that will use this theorem, so I wanted to get it out of the way as just writing it down. So simply we're going to have a homogeneous system of n linear equations and n unknowns, so that just means all these values on the right are 0. I'm hoping you like come across homogeneous systems before. If not, you can check out chapter 0 or something, but I'm just going to assume that's like known. So in this case we have a result, so we have this system of homogeneous equations, a homogeneous system of linear equations. In this case we have that 5.1 has non-trivial solutions. I'm going to use this symbol, if and only if, covered in chapter 0, if not, that's what it means, if and only if. That's the same as this symbol, by the way. They're analogous, it's just what feels more flowy. I kind of felt if and only if. It felt like an if and only if moment with this one. So 5.1, this equation here, this system of equations has non-trivial solutions if and only if. Wait, let me check my notes to make sure I get this right. The determinant of A, which is the matrix, is 0. So this is not at all an obvious result, but it's very, very useful, and we'll be using this in some proofs, but I'll come back to it when we actually use it in the proof. For now, I'll just sort of put it as a side note. And also I'm hoping you know about trivial, non-trivial solutions and homogeneous systems. If not, as a brief recap, the trivial solution is x1 equals x2 equals x3. Equals xn equals 0. That's the trivial solution of a homogeneous system of equations. And we're saying that the determinant of the matrix links to the fact that when the system will have non-trivial solutions, which when you see the definition of linear independence, it will become obvious why this theorem is so useful in proofs regarding them. And then I just want to have a quick look at the negation of this theorem very, very quickly, just so that we have this for later on. So since if and only if, in terms of equivalence, it has non-trivial solutions when it's 0, so you can imagine the negation is... I've already read it out, so yeah, just we can read it. 5.1 has just one trivial solution, if and only if determinant of A is not equal to 0. And this one is a lot easier to prove than the theorem, and in fact we can probably see the result right now why that's the case. So det A not equal to 0, that means it has an inverse, so simply you do the inverse on both sides, and you get that the only solution is x equals inverse A of 0, which is just the trivial solution. So there's a quick proof of the corollary. And so that is all for now on that. These were kind of the preliminary things I just wanted to get out of the way, so we have them for later, and so I've covered them. Just so we're all on the same page of what kind of linear algebra stuff is not immediately obvious that we'll need in the proofs. Okay, and now we get to the main meat, which is definition, what are we on? 5.5, and this is going to be the big boy definition. We're going to do a definition of linear independence, what we all came here for. And I'm going to be quite bold on how I'm defining this, and we're going to use a terminology that might prove to be a bad idea, but I can always re-record this episode of this chapter if it's not a good idea. But I think that linear independence, what does that mean? And the more you look into it, I think there is intuition, but I think it takes a good maybe week or so of doing problems until it starts to click what it means to be linearly independent. I don't think that's linearly I don't think that's the most natural concept ever. So I think using alpha flavored until you see some examples and then switching to this terminology when it becomes clear what that even means is better, because this, when you think about it as alpha flavored, because it clearly doesn't mean anything at all, it forces you to refer back to the definition, which I think is a really good thing for problem solving with this topic at first. So enough pre-ramble, let's look at what the definition is. And I've seen this definition enough times, I shouldn't get it wrong, but I had some notes on how I wanted to write it. So first of all, we'll have a vector space. Good start, given this is the vector spaces series. So we'll say let V over a field be a vector space. And then we have then set A equals U1, U2, up to UK, where K is some natural number. So I have a set of vectors, and we're saying this set of vectors is a subset of V. Then we we're going to bind some variables here. So we're going to say for lambda 1, lambda 2, up to lambda k. So we've got as many scalars here as we have vectors in set A of the set of the field which the vector space is over. So for these scalars and for this set, here's the punchline. We say A is now I'm going to use my terminology. I'm going to say A is alpha flavored, or to use the proper, the posh words, it would be to say it's linearly independent. And then we're going to have a bit of logic here to define when we say it's alpha flavored, and we're going to define it logically as using our scalars we have lambda 1 U1 plus lambda 2 U2 plus or up to lambda k UK, and we're going to have this equal to 0, and now we're going to say when is this equal to 0. We're going to say if and only if wait, I should make sure I get this right. This is the case when only when lambda 1 equals lambda 2 equals lambda, could do lambda 3. Yeah, let's do lambda 3, why not? The point is we've got a bunch of lambdas, we've got precisely k of them where k is some natural, and we're saying all of these are equal to 0. And this is precisely what we mean by being alpha flavored or linearly independent. So what can we say about this definition? First of all, it's a definition, so we can't prove it. Like, it's quite dense to word out. Like, that's not a quick and easy definition to cater around. Although in practice, you're only really going to use this only going to be using this section at the end here, seeing as you'll usually have the vector space we're working with, like implicit or explicitly defined, and you're just working on showing that this is alpha flavored. That's the first thing. The other thing to note is that this double arrowed is literally equivalent to, so if we name this the left hand side and we label this the right hand side, this double arrow is the same as saying left hand side implies right hand side and right hand side implies left hand side. And the reason why I'm drawing attention to this is because when we're going to write out our definition for linearly dependent or beta flavored, we're going to show that the definition is literally just a logical negation of this definition. And I might save that for, I'm going to take a quick break and then come back for that. Okay, so we continue. So we've looked at alpha flavored, so it makes logical sense to now look at definition, what number we are, I think 5.6. One of these days I'm going to remember the number, 5.6, which is beta flavored, is the way I like to call it, just while you're beginning getting used to the definition. But as it's formally called, it is, I'll just put it here. It's the opposite of linearly independent, so it's linearly dependent. You can also say not linearly independent if you wanted to think about it that way. So same setup as this. So we're going to have let a vector space B, and then we're going to, and I'll try and go through this quick because we've done this before, then, and maybe give it a different letter, Let's give it a different letter, why not? What's not confusing? Go with C just for why not. Then set C, subset of V. Oh wait, yeah, I should write what vectors are in actually because we're going to be using that. Let's set C equals U1, U2 to UK, a subset of V. What are we doing? Oh, and then it's a bit weird to word it so that we can make it as concise as possible. For again, lambda 1 up to lambda k. We say C is eta flavoured brackets linearly dependent. I worded it before. Oh, I did a colon, it's a good idea. Let's do that again. If we have lambda 1 U1 plus lambda 2 U2 plus up to lambda k UK equals a zero vector, but this time we're going to say does not imply that lambda I equals 0. How am I going to word this? Before I equals 1. Okay, so I could be any of the 1 to k, so any of these lambdas basically. If we can show that it does not imply, and that essentially means is that we'll find one of these lambdas is not 0 when this is true. So adding them up gets a 0 vector, but one of the lambdas wasn't 0. In other words, a non-trivial solution, hence why I covered that in an earlier theorem / corollary. But this isn't the full story, like we discussed not long ago with the left-hand side implies right-hand side and right-hand side implies left-hand side. The logical negation is that as left-hand side does not imply right-hand side and right-hand side does not imply, right-hand side does not imply left-hand side, so we're going to use that here. So the two definitions really are just the same, but just inverses of each other. If you want to think about it that way, you don't have to, obviously. Or lambda I equals 0. Maybe it's clearer. Oh, I've got auto shapes on. Whoops. Maybe it's clearer if I put for all actually, just to be extra clear. For all I equals and then that. And we can use the for all symbol. Equals 1 to k. Does not imply. And then try and save some time. Maybe try and copy paste that. Is that going to go well? Might not go well. Can't lie. Yeah, that went okay. A little bit of graphical engineering. Okay. So yeah, so you can do it either way. You tend to use the first way, so some textbooks you'll see just this, but technically you can do either. Showing either is enough to show that the set is beta flavored. So you can bear that in mind if you want. Okay, so enough definitions wise. Hopefully that's all clear, and you can use either term. Obviously in exams you'll have to say linearly dependent, but you'll get used to it when you do practice questions. And when you see the proofs in episodes 3 and 4 of this chapter, like, you'll see why I prefer to use this for proofs, because it gets so dense that it kind of helps to remember very quickly which definition you're referring to. And these words can get like confusing in your head. Maybe I just don't like words. It's possible. Okay, let's move on. And so now we get on to the two big theorems of this chapter. Both of which are important, but I think the first one I'm going to go into, I think, hopefully, will bring a bit of wonder to this topic, because it has been a lot of logic so far. So hopefully this will be interesting at least. So this is going to be proven in episode 4, and this is going to be the big one, as opposed to the next one, which is going to be big. I'm also going to label it as quite fundamental, not very, but quite, for reasons we'll see in the bases chapter. Okay, so let's do it. So, good start, we're just going to say let a vector space then what we're going to say is you can use different symbols for this. I'll make sure I use the correct symbol. So we'll do the linearly independent slash whatever one first. So let T let's first of all say what it is. So we've got where's my cursor? There it is. Let set T subset of V, and that's actually all we need to do is say that it's alpha flavored. Be alpha flavored. Okay, that's our set T. I forget how quick you can write this theorem. It's like, given how like significant. I think that's why I like it as a theorem, because it's really quick to write but quite tricky to prove, which I think is what the best results are. Easy to ask the question but very hard to answer. Let's set S of S of V, our vector space, and in this case we're going to be I'll use such that. Remember in the spanning sets chapter we said that means spans, S spans V. And then this is literally it, one more line, then we're done for this theorem stating what it is. The cardinality or slash the size of T in terms of how many things are in it is always going to be more equal to S. And since we've made these sets very, very, very fundamental, these are any sets so long as T is alpha flavored and S is a spanning set of V, then boom, this holds. Which, yeah, it's pretty cool, I think. And we'll be proving that in episode 4. And so, if you're just interested in the theory and less so on worked examples, I would skip episode 2, probably skip episode 3 as well and go straight to ep 4. But if you want some worked examples, that'll be in episode 2. So that's the first big theorem. I don't think there's anything else I want to say about it just yet. I think we'll come back to it and make some comments later when I see how long I've spent on this. So I don't want this episode to be over half an hour if I can avoid it. Alright then, so now we're going to look at theorem 5.8. So I'm actually recording over this section of the video because I made a small error in my writing of this theorem, which is quite important. So this theorem we're going to be proving in episode 3, and this is the lesser of the two theorems in this chapter. And now I'm going to write the whole theorem out again, but I'm going to do the correction of what I got wrong in the original in blue. Okay, so like we did with the first theorem, we're also just going to say a vector space exists, because that's just a good step with these vector space based theorems. So we've got let V over field F a vector space. Alright. And then we're going to set up a set again. In particular, we're going to be focusing on two sets in this theorem. So we're going to have let set A. Oh wait, I almost missed this. Yeah, there's a lot of like weird technicalities. I really don't like this theorem. Like, it's a fun theorem and it's alright to prove. It's got some interesting parts to proving it, but writing it out is so technical. And like, I feel like the less general a theorem is, and the more technical it is, like the less interesting it is. Like, you want broad, useful, general theorems, right? This is not it. So a clarification that we need to make on this is that V is not equal to just 0, but V can still contain 0. So for example, so the vector space is going to be bigger than 1, we know that. And when it is bigger than 1, 0 will be in V. It's just we can't have V being just 0. That's important for this. So let set A be a subset of V, and oh yeah, there's 3 things. So we've got A is a subset of V, we got A spans V, and this is the bit that equals. So span of A equals V, and then this is the bit I missed before, so we'll do this all in blue. And the 0 vector is not of the set A. So in other words, all the vectors in A are non-zero. So yeah, this doesn't work unless this is the case. So when you see me scrolling past this theorem, when I go back to the main video, just imagine this blue bit is also on there. But yeah, sorry about that. Okay, so we've got A of V, and A is spans V, and 0 is not of the set A. In this case, we have that. So right then, there exists B, a subset of A, such that, put it on the next line, B spans V, and B is alpha flavored. So it's an okay theorem. The idea is that it links the two parts together in another way to this theorem. And it just means that you use this in worked examples sometimes, but it's like the thing with this theorem is it's like really fundamental to proving like the key result we have in the chapter 6 on bases. So like this directly comes into play in the main branch of theory, whereas this just kind of sits on the side and kind of gets put in this theorem's shadow, in my opinion. But it is cool. It brings the two together. Suddenly we have alpha flavoured appearing out of trying to take a subset out of A, which has these properties. But it's just too wordy for my liking as a proof. Okay, we're going to go back to the main branch, but yeah, just try and like imagine you had this bit's here. Sorry about that. Bye. And so that's why I'm going to prove this theorem first, because I think it's a little less work. This is really quite some hard work to prove, by the way. But I think it's worth it, so if you fancy seeing some dense logical proof stuff, then that'll be good. But it might go as long as like 40-45 minutes, because there is a lot of stuff to be done here. But like for me personally, when I like wrote out and worked through this proof, like this is a big claim, but I honestly felt like I was a better mathematician after doing it, which is why I'm hoping that like if you join me for me doing another one of proving this, you'll get something out of it in terms of what it means to do really hard proofs and how you go about it. Like I can't imagine the guy who first figured it out. It'd be crazy to be inventing all this like abstract algebra stuff when there's like nothing for you to base it off of. Okay, and this is really the main content of the video. All we've got left is two like really not important points. So I guess for a lot of you guys, you'll want to go on to episode 2 now, or on to episode 4 if you want to see that proof. But for the rest of you who are interested in seeing everything I wanted to cover here, if you want to get like the full educational experience of this episode, we have 2 more quick things. So first of all, this might be too basic, but just in case, because like I thought this was, I think it's nice to be thorough in maths, and although it's simple, I prefer to cover everything, even if it's a little bit too simple, as opposed to not cover it, you know. And it gets used in the proof, and in the proof there's a more complicated example. This is going to be a very, very simple example, but just because there's a more complicated example in one of these proofs that took me a good long time, like maybe like 10-20 minutes. I mean, it's not that long, but like of looking at it being like, oh, why is that true? I'll come back to this when I get to that, but yeah, you're gonna laugh at me for how simple it is, but honestly it can get complicated sometimes. So just to clarify, so you got A and B of real, and then what we can say is that A, if we're saying A bigger than B, the negation of that statement is that A smaller than B. And you know, I'm not going to say any more on that, just that's something to bear in mind. I think the thing that threw me with this, especially when it gets more complicated, where you have more variables involved, is that this isn't really this isn't necessarily true or false. This is more just a thing you can say, and the fact you can negate that kind of threw me a little bit, because we're going to be doing like proof by contradictions for both of these. So this kind of thing is going to be useful to us. That's just a quick point I wanted to dump there. And then finally, one last thing, and then we're done for today. Idea 5.10. This is a little bit more advanced, but not really. But also just interesting. I've never really seen people do this, and it seemed useful to me. There's probably a good reason why you don't see this so often, but so consider you have some m of the real numbers. Yeah, I'm going to draw a diagram. Why not? Although this diagram's not going to be that useful to us because I don't know why I'm drawing it. Oh well. M can be any real number. It doesn't have to be positive or negative. Because the trouble is there's too much going on for the diagram to actually be useful. Then we're going to have a new variable we're going to bind. So we're going to say let k of the set 1 to m intersecting with integers. And so what this means is that k is between 1 and m and it's an integer. And this seems like a really neat, concise way to write that. And I've not seen it before. I don't know why. I guess maybe people usually first say k of the set of integers, then say k of the set of 1 to m. But then this seems like it's harder to keep track of, and maybe it's just like imply k is an integer and always will be an integer, so you can do this. But then I don't really see this either, so I don't know. Let me know what you think in the comments if you know why you don't really see that so often. And just to like explain why this to me like seems like a good idea. If you were to like, because I like the idea of doing it in 1 line, doing it in 2 lines seems kind of stupid as well. But if you were to do it in 1 line without using this notation, it would be like this. And say let k of the set, and you could use a different dummy variable here, but I don't see any reason to. I think it's perfectly clear to just use the same variable. It's clear that it's a different scope. You'd have to do it like this, say k is an integer, and then such that it's between 1 and m. And I don't think either of these are nice options. So in my proofs of these 2 theorems we've looked at, sorry I kind of moved up and down a bit fast there, but you get the idea. We did some theorems back there, 2 of them, that in the notation we often need a variable to be bound between 2 things and to be an integer. And just the last thing before I end this video is just an example of how this notation works. It's probably pretty clear already, but just in case it's not, let's say m was 3.2 for example, then what we're saying is k is some number of the set 1, 2, 3, because those are the 3 integer points that are between 1 and m. So yeah, thank you for joining me, guys. I think I achieved it, less than half an hour, but I haven't recorded my preamble. I'm recording this in parts. I'm recording it in 3 parts. I've done part 1 and 2 now. I'm going to go back and do part 1 part 1. I've done part 2 and part 3, and I'm going to do part 1. So if I don't speak too long, I can keep this video under half an hour as the goal. But I should stop talking now, so I've got time for that intro. Just to highlight you what's going on. So we've got episode 2, worked examples. And then we already discussed episode 3 and 4 will both be proofs. There might be an episode 5, I'm not sure what will be in it, but something maybe. Yeah, and I think seeing at least one of the proofs is worthwhile. I think this is a more interesting proof, but it's definitely a bit harder, so I don't know. Choose as you will. Bye!